Hello ladies and gentlemen, my name is David Hills, the Scientific Director for Separation Science, and I'd like to welcome you all to our latest webinar in collaboration with Sapelco Sigma Aldrich. Our topic today is choosing the right adsorbent for your thermal desorption gas chromatography applications. So with that out of the way, let me introduce our presenter for today's webinar. Jamie Brown is an R&D scientist with the Sapelco division of Sigma Aldrich. He has over 27 years of experience in the development of products for sampling organic volatile compounds from air and water. Jamie has routinely assisted regulatory agencies such as the US EPA, OSHA and NIOSH with method development, and he's an active member of the ASTM D22.05 Air Quality Committee. He has collaborated on methods for domestic and international regulatory agencies through Sapelco's global network of subsidiaries and research partners. And so, without further ado, I'll turn the presentation over to Jamie Brown. Jamie?
Thanks, David. Hello, everyone. Thank you very much for attending our webinar today. We really appreciate it. We know how time is busy, and we really appreciate you making some time for us today. Our goal is to provide you with some useful information about choosing the right adsorbent for your application. The topics that we'll discuss today are related to the adsorbents and sampling conditions. A little information about single bed and multi-bed tubes, characteristics of some of the adsorbents, flow rate and linear velocity, sample volume, back pressure, and humidity. So first I need to cover a little bit of what is thermal desorption, and it's a sample preparation technique for gas chromatography. The sample is collected onto an adsorbent-packed glass or stainless steel tube. Then that tube is placed in a thermal desorber where the packed tube is heated and the compounds are released into the carrier gas where they are swept onto the GC column and analyzed by a gas chromatograph. In most thermal desorbers, there are two tubes. There's the primary tube, which is the tube that we're using to collect our air samples from the field, and then built into the thermal desorber is a refocusing tube or a secondary tube. The primary tubes have IDs of typically 4 to 5 millimeters on ID, and the secondary trap has a smaller ID, which is 1 to 3 millimeters. And the purpose of the secondary trap is to improve the chromatography of the very light compounds. Thermal desorption can be used to sample most organic compounds. There are a few exceptions, and those are compounds that are sensitive to thermal degradation, compounds that require derivatization prior to analysis, like formaldehyde and isocyanates, compounds that are larger than C40, and there are a number of methods where thermal desorption is used today, such as EPA T01, T017, NIOSH 2549, ASTM D7339, and D6196. And the Health and Safety Executives out of the UK has MDHS 80, and these are just a few examples where thermal desorption is used. So on to single bed tubes. Single bed tubes are a single adsorbent packed into a glass or stainless steel tube. In this example here, it's a glass tube, and the sampling inlet is on the left, and right before the adsorbent we have something like a glass frit to hold the adsorbent in place, and that kind of defines the heated zone of the tube. At the other end, at the outlet, we have a glass wool plug and a stainless steel clip to keep everything secure in the tube. The heated zone of the tube is usually around the center of the tube, and the ID of the tubes are typically 4 millimeters. ODs can range from 1/4 inch to 6 millimeters depending on the thermal desorber. Single bed tubes can be used for both active and passive sampling if the tube itself has been designed for passive sampling. So when we take our air sample, the sample enters the inlet and our airstream travels through the adsorbent out the outlet of the tube. And then during desorption, our flow is reversed where the carrier gas pushes through the outlet of the tube, through the adsorbent, and then back in through the inlet, and then our analytes are released into the thermal desorber. Then a multi-bed tube. In a multi-bed tube, we can have anywhere from 2, 3, 4 beds are typical. And the example here is a 3-bed multi-bed tube, which is our Carbotrap 300. The adsorbents are arranged from weaker to stronger from the inlet side. The last bed is often packed with a stronger adsorbent like a carbon molecular sieve. Where multi-bed tubes can only be used for active sampling, since the compounds cannot travel through all the adsorbent beds without the help of an air sampling pump. So then we always have the choice, glass versus stainless. Glass has the advantages that glass is typically considered more inert. We can see what's going on inside the tube as it ages. The glass frit in the inlet keeps the adsorbent in place during use. And one of the disadvantages, of course, with glass is they commonly break. Stainless steel tubes, the advantage are the tubes do not break. The ID is typically a little larger on a stainless steel tube, which will allow us a little higher flow rates that I'll cover later on in the presentation. And one of the disadvantages is as the tube ages, we can't see what's going on inside the tube and see if the adsorbents are moving. And now I'll cover a little bit about the characteristics of a good thermal desorption adsorbent. Adsorbents should be able to retain and release the compounds of interest, should be able to withstand high temperatures at around 300 degrees C, should have low background levels, should have low metal content, should be hydrophobic, and some more desirable characteristics is they should have consistent mesh sizes, consistent densities, low shrinkage, and low amount of fines created during use. Often I'll talk to customers and they'll just ask for the strongest adsorbent available. And will that work for everything? And the answer is no if we're trying to sample a broad range of compounds. Some of the things that can occur is irreversible adsorption, poor desorption efficiency for the larger molecular weight compounds. And usually it will require a large dry purge volume if sampling in a humid atmosphere. And we'll have more solvent interferences if we're using liquid standards such as methanol standards made up for our calibration. In this example, the top shows a desorption of 43 compounds that were spiked on a tube just packed with carbosiv S3. And the compounds range from chloromethane being the lightest at 50 molecular weight to hexachlorobutadiene at 260 molecular weight. And as you can see at the end of that, the part where I show where the poor desorption efficiency is, these compounds were irreversibly absorbed by the carbosiv S3 compared to the bottom, which is the same compounds in the same concentration spiked onto a multi-bed tube, where we get good release of those heavier molecular weight compounds. If you compare the gases from both of those chromatograms, they're equally recoveries pretty close to each other. So if we had a tube just packed with carbosiv S3, we're only going to get good release of those lighter molecular weight compounds. So we'll define some terms. Surface area provides a general idea of the adsorbent strength, but it doesn't provide the whole picture. Other characteristics such as pore size, pore shape, porosity can also play a role in the adsorbent's ability to retain and release different compounds. One rule of thumb is the higher the surface area value, the stronger the adsorbent. However, when the surface area is greater than 800 meters squared per gram, the size and shape of the pore becomes more important. The surface area is a measure of the exposed surface of an adsorbent on a molecular scale. And another generalized rule is the adsorbents with surface areas less than 200 meters squared per gram are good to trap and release compounds that are a liquid at room temperatures. And those with a surface area greater than 500 are good to trap and release compounds that are a gas at room temperatures. But of course, there's always some exceptions to these rules. Pore size. Pores are classified according to 3 main groups depending on their size. As a general rule, an adsorbent containing larger macropores are used for large semi-volatiles, and those with mesopores are used for volatiles that are liquid at room temperatures, and the smallest pores, the micropores, are used for very volatile organics and inorganic molecules that are a gas at room temperature. In times there's things to complicate things, or the molecules of interest have different shapes and sizes on their own. For example, the freons with a large chlorine atom are in a gas phase at room temperature, but oftentimes we can retain them using a weaker adsorbent such as one of the carbopacks. So using a multi-bed tube that contains different types of adsorbents will always allow us to collect a broader range of compounds from a single tube. So now I'll cover some of the adsorbent types used in thermal desorption. And there's basically three classifications that are pretty typical, and those are porous polymers, graphitized carbons, and carbon molecular sieves. First I'll cover the porous polymers. Porous polymers or adsorbents are generally granular in shape. All porous polymers can be considered hydrophobic, and oftentimes the porous polymers can have higher background contamination, making it sometimes hard to reach low part per billion detection limits. 10xTA is the most popular adsorbent used in thermal desorption. Its maximum temperature is around 350 degrees, and we recommend desorption temperatures around 300, and when we go to condition the tubes, we recommend 320. Since methanol is not retained by methanol or by 10x, it's a good for spiking tubes with liquid calibration standards. Some other common porous polymers are Poropac N, Chromosorb 106, and Hasep D. They have relatively low maximum temperatures of 225 to 290 depending on which porous polymer, and lower recommended desorption temperatures. Now I'll cover the graphitized carbon blacks. They have a maximum temperature of 400 degrees C, a recommended desorption temperature of 330, and a recommended conditioning temperature of 350 degrees. Methanol is also not retained by most of the graphitized carbon blacks. And graphitized carbon blacks are pure carbon granular in shape. They're manufactured at temperatures that exceed 1200 degrees C and exhibit graphite-like properties. Most of the carbopacks, except Carbopac X and Z, are non-porous. Since most graphitized carbons don't contain any pores, adsorption takes place by London dispersion forces, which exist between the molecules and the adsorbent. Carbopac X is one of the strongest graphitized carbons, which bridges the gap between the other carbopacks and porous polymers and the stronger carbon molecular sieves. All of the carbopacks are very hydrophobic, so they're a good candidate when sampling high humidity environments. And graphitized carbons typically have fewer impurities than charcoals, making them more inert and useful for trace analysis. However, the carbon particles can be fragile, so you should try to protect the tubes from rough handling in order to extend their life. This slide shows the adsorptive strength of the graphitized carbon blacks, and Carbopac X being the weakest with 5 meters squared per gram to Carbopac X with 240 meters squared per gram. Carbopac X doesn't have much surface area and has shown good promise for releasing those compounds that are reaching into the semi-volatile range. And the Carbopac X is doing a very good job of the compounds that are midpoint boilers and very light compounds. What you're looking at is the recovery of 43 compounds from different carbopacks. The mixture contained a range of compounds and molecular weight from chloromethane to hexachlorobutadiene. The first chromatogram in blue is the calibration standard from a 3-bed tube. As we proceed down, notice how the lighter compounds are not retained. And the Carbopac X did a great job of trapping the very volatile compounds, but the recovery of the last two compounds is poor, showing that Carbopac X is too strong for these two compounds. They were irreversibly adsorbed. And then the bottom in white is glass beads, and you can see it only trapped the high molecular weight compounds, and in fact these even had broke through. Sometimes we get the question, what's the difference between carbotrap and carbopack? The only difference is the size of the particles. After the adsorbents are manufactured, they're placed in sieving screens to collect the various sizes. So carbotrap always is the larger particle sizes at 2040, and then carbopack is 40, 60, 60, 80, and smaller mesh sizes. The carbon molecular sieves, they too have a maximum temperature of 400 degrees C, a recommended desorption temperature of 330, and a recommended conditioning temperature of 350 degrees C. They're spherical, other than one of them, carbosieve G, is granular. They have a shiny dull black color, and they have a lot of surface area. And they're designed to retain and release smaller molecular weight compounds. In most applications, a weaker bed of a porous polymer or a graphitized carbon black should be placed in front of it to keep the heavier compounds from becoming irreversibly absorbed. The only time a carbon molecular sieve should be used by itself is if we are confident that our sample doesn't contain compounds with boiling points greater than benzene. This chart provides a general overview of the difference in strength of the carbon molecular sieves. But in some cases, for certain compounds, you'll find some differences. Those in blue are the most commonly used carbon molecular sieves. And there's a couple other adsorbents. Glass beads perform well in releasing large molecular weight compounds greater than C20 and can be used as the first bed in a multi-bed tube to protect the other adsorbents, and they have a high maximum temperature of greater than 500 degrees C. Some other adsorbents have been used, but they're not typicals. Like charcoal are typically not used for thermal desorption since they tend to retain the compounds too strongly, and they don't release them well using thermal desorptions. And charcoals can have metal impurities that, when heated, can cause decomposition of some compounds. They also have a lower maximum temperature, which also limits their use. Silica gel is typically not used for thermal desorption due to its large affinity for water. They don't dry purge well, and they too have a low maximum temperature of about 190 degrees C. Mold sieves also have a large affinity for water, thus they're not very thermal desorption friendly either. So now I'll cover a little bit about adsorbent mesh size. Does the adsorbent mesh size matter? It is a very important consideration when we're packing adsorbent tubes, is the relationship of that particle size to the ID of the tube being packed. The best efficiency occurs when the ratio of the particle size to the ID is between 0.1 and 0.25. This chart shows the ratio of the particle mesh size and different tube inner diameters. So, for example, a 4 millimeter ID tube, the optimum ratio is met with 2040 mesh particles. 10 mesh particles in yellow there are too big, and there's a good chance that channeling will occur when we're sampling. And if we use the 60 mesh in smaller particles, they're smaller than we need, so the back pressure will be too excessive. And oftentimes you'll see 1 millimeter and 2 millimeter refocusing traps packed with 60-80 mesh because they fit that ratio of the particle ID to tube ID very well. And sometimes you'll see carbon molecular sieves of the 60-80 mesh packed into the larger 4 millimeter and 5 millimeter tubes. And this is simply because when the adsorbent is manufactured, the process doesn't yield particles larger than 60 mesh. So how does mesh size affect back pressure? Compared to other air sampling media, thermal desorption tubes usually have a higher back pressure than the traditional solvent desorption tubes. And oftentimes you'll hear me reference back pressure and pressure drop, and they mean the same thing in terms of this presentation. For this experiment, the heated zone of the glass tubes were filled with the same volume of each mesh size of Carbopac B. Then the back pressure was measured for each tube at different flow rates. So for example, with a 2040 mesh Carbopac or Carbotrap, in the flow rate of 250 mils per minute, we had a back pressure of 7 inches of water. When we move to a 4060 mesh material, the back pressure increases to 17 inches of water, and for 6080 it increased to 42 inches of water, and for 8100 it then increased to 48 inches of water. So what does this all mean? This usually, our problem with back pressure is due to air sampling pump capacity. Most of the personal air sampling pumps are battery powered, and they have a back pressure rating that they can handle anywhere from 8 to 35 inches of water depending on their brand and manufacturer. So if an air sampling pump can only handle 18 inches of water, the theoretical flow rate that we could achieve with the different mesh sizes are the following. A 2040 mesh, we could achieve 545 mils per minute, and with a 4060 mesh, we could get 216 mils per minute, and at 6080, we could get 86.5 mils per minute. The shape of the adsorbent particle also plays a role. The spherical particles will have the same space between all of the particles, whereas the space between the granular particles is different. The more you pack it or vibrate it, the higher the pressure drop. So as you can see, the granular adsorbents have more back pressure than spherical adsorbents on the same mesh size. And this helps explain why the pressure drop can change as the tubes are used over time. The granular adsorbents can continue to pack tighter as they are handled more often. So now we'll cover a little bit of information about flow rate and sample volume. Linear velocity. I don't want to get stuck on the details of linear velocity, but it's an important parameter to consider when setting up your sampling protocol. The important takeaway is that we need to allow enough time for our compounds of interest to interact with the adsorbents. As the tube ID gets smaller, the linear velocity becomes faster at the same given flow rate. A good analogy is to think of thermal desorption tubes as little packed chromatography columns where the tube is the column and the air we're sampling is the carrier gas. Based on the Van Diepter curves for packed columns, the best efficiency is obtained when the linear velocity is between 10 and 20 meters per second. So for a 4 millimeter tube, this correlates to an optimum flow rate between 30 and 60 mils per minute. So we want to try to develop our sampling protocols close to the optimum flow rate for the ID size of the tube we're using. This next slide demonstrates this with a little bit of animation. Here the velocity is calculated in centimeters per minute for the demonstration. Just like a packed column, the smaller molecular weight compounds will be the first to migrate off the tube if the flow rate is too fast. The top is the linear velocity of a 4 millimeter ID tube, and the bottom is an 8 millimeter ID tube. Notice both tubes have the same flow rate of 25 mil per minute, but the linear velocity is 4 times faster with the smaller ID. So what sampling flow rate should I use? Well, 50 mils per minute is a good starting point, and this is within the range of the optimum linear velocity for a 4 or a 5 millimeter tube. But there may be times where we need to collect a larger volume of sample in a shorter period of time, and a flow rate of up to 250 mils per minute may be necessary. Just keep in mind that you could start to lose some compound sampling at or above this flow rate. One way around this is to switch to a tube with a larger ID, and the linear velocity would be slower with the larger diameter. So what sample volume should I collect? Some recommendations for a single bed tube with a hydrophobic adsorbent, and that would be anywhere from 1 to 10 liters. When we get it with the multi-tubes with the carbomolecular sieves that can retain a little moisture while we're sampling, we want to reduce that flow rate to our flow volume to about 1 to 5 liters. And if we've got a multi-pad tube packed with a hydrophilic adsorbent such as silica gel or mold sieve, we'll want to really limit that sample volume to reduce the amount of water we trap, from a half a liter to 1 liter. So humidity. Most of the time when we're sampling, humidity is always present at some level. And humidity causes us some problems. Problems during sampling are water vapor can be retained by the adsorbent, it can mask the available site of the adsorbent, and can in some cases displace the compounds. Problems during the analysis, water vapor can alter the split flow ratios during the desorption, can create chromographic separation issues, can blow out the FID flame, and reduce the vacuum of an MSD detector. So we need to keep humidity in mind when sampling, since the quantity of water vapor is often at milligram levels, and the compounds of interest are often at nanogram levels. So how much water is in the air? This chart shows the absolute humidity at various temperatures and relative humidity levels. The absolute humidity will tell you how much mass of water is contained in each liter of air sampled. So as an example, if the relative humidity is 60% and the temperature is 25 degrees, there will be 14 milligrams of water for every liter of air we collect. So silica gel is hydrophilic, and it will retain 40% of its own weight in water. So this is why silica gel is not typically used for thermal desorption applications. Some adsorbents are more hydrophobic than others. 10X, Carbopac, Carbotrap are very hydrophobic, and virtually no water will be retained in them while sampling in humid conditions. Carbomolecular sieves are still classified as hydrophobic, but at high humidity, some water is retained, but the bond to the water is weak, and it can be driven off at ambient temperatures using a dry purge prior to analysis. So how much water is retained by Carbopacs and 10X during sampling? In this experiment, we packed a heated zone of glass tubes with the same volume of each adsorbent, conditioned them, then subjected them to an atmosphere where the relative humidity was 75% and the absolute humidity was 17 milligrams per liter at 25 degrees C. This chart illustrates how much water is retained by a few Carbopac and 10X TA and a newer carbomolecular sieve called Carboxin 1016. The solid blue line is the total amount of water being collected by a silica gel tube. So after sampling 2.5 liters of air, the amount of water retained on any of the adsorbent fluctuated somewhere between 0 and 3 milligrams, which isn't very much. But the silica gel tube collected 43 milligrams of water in a 2.5 liter sample volume. So virtually no water is being retained during the sampling with the Carbotraps and 10X material. So they'll require very little dry purge prior to analysis. In this experiment, we show how much water is retained by Carboxin 1000. For this experiment, we packed the tubes with Carbopac B and different amounts of Carboxin 1000, which is a carbon molecular sieve. The relative humidity for this experiment was 80%, and the absolute humidity was 18 milligrams per liter. The solid blue line is the total mass of water being collected by the silica gel tube, and after sampling 2.5 liters of air, the amount of water retained by the tube with the least amount of carboxin was 16 milligrams of water, and the tube with the most amount of carboxin retained 18 milligrams of water. The silica gel tube collected 46 milligrams. So notice how the amount of water retained by the Carboxin 1000 begins to level out compared to the silica gel that continues to retain more water as more air is collected. This chart shows the relative humidity, or relative hydrophobicity of the adsorbents I've covered today, being glass beads being the most hydrophobic and the most hydrophilic being the silica gels and mold sieves. The carbomolecular sieves are kind of in the middle, and if we're sampling any amount of humidity, this will always require some kind of dry purge. So that leads us into dry purge prior to analysis. The key to dry purging is allow enough dry gas to pass through the tube and carry the water away. But too much dry purge can actually start to push the compounds of interest through the adsorbents, thus we'll get some breakthrough. So some recommended dry purge volumes for a few types of adsorbents. 10X, carbotraps, carbopacks typically only need 1/4 of a liter, regardless of the humidity level. But carbosieves and carboxin adsorbents may need 0.5 to 3 liters of dry purge, depending on the absolute humidity level. So some practical ways to determine the required dry purge volume. Prior to sampling, we'd weigh the adsorbent tube, and record its tare weight. After sampling, we'd reweigh the tube. If the difference is greater than 1 milligram, then dry purge is required. So then we'd purge the tube with clean nitrogen or helium at around 50 mils per minute. After a half a liter had passed through the tube, we'd remove it and reweigh the tube. We would repeat this every half liter until the tube weight is within 1 milligram of its tare weights prior to sampling. So most GC systems can handle 1 milligram or 1 microliter of water if the thermal desorber is splitting some of the sample. So once you've went through these steps, this could then, dry purge volume could be automated in your thermal desorber once you know the volume you need to dry the tubes. So here at Sapelco, we offer some more literature to help you pick and select the right adsorbent for your application. This report provides thermal desorption users a tool in choosing the right adsorbent for their application. It demonstrates the relative difference between the most commonly used adsorbents in the field of thermal desorption. It includes adsorption and desorption data for 43 common air pollutants on 24 different adsorbents. We challenge the adsorbents with 6 different sample volumes ranging from 0.2 liters to 100 liters, and the recovers are displayed in 3 different colors. This mimics the color of a stoplight signal, with green being very good, yellow warning, and red not recommended. So in conclusion, there are 3 main types of adsorbents used in thermal desorption: porous polymers, graphitized carbons, carbon molecular sieves. And there are many factors to consider when choosing an adsorbent: single bed versus multi-bed, range of compounds to be sampled, sampling flow rate, sample volume, dry purge volume. And here are some trademarks of those adsorbents that I mentioned. And I've got some acknowledgments. Here's some folks here at Sapelco. I think there's some people out in the audience I'd also like to thank. And I also can't forget to thank all of you for listening to this webinar today. And I think we're now ready for the question and answering section of the presentation.
Well, thank you, Jamie, for that excellent presentation. Before we move on to the Q&A session, we have an interactive polling question which is open for all attendees to participate in. You should now see a pop-up box on your screen which includes options relating to follow-up materials from Sapelco Sigma Aldridge. This box will remain on the screen for a few minutes, so if you're interested in receiving any of this follow-up information, please do select your options by clicking the relevant buttons. So, Jamie, now we can move on to the questions received via the Q&A box. And for those of you listening who have questions, now would be a very good time to send them in. So, Jamie, our first question today is, I'm looking to trap 1,3-butadiene. Which adsorbent should I use?
Dave, that's a good question. There's 2 adsorbents that's showing a lot of promise right now, and that's Carbopac X and Carboxin 1016. There are some methodology using the mole sieves also, but because of the moisture problem, maybe the Carbopac X or Carboxin 1016 might be a little more user-friendly. Okay, and the next question we have is, what is the effect of desorption temperature on compound recovery? Ultimately, if we can get our desorption temperature as high as possible, we'll get the quickest release from the adsorbent onto our GC system, which optimally gives us the best chromatography. So if we have to have lower temperatures, we might see a little band broadening occurring, and that can help, that can reduce our limits of detection.
Okay, and the next question is, what adsorbents can trap the broadest range of compounds?
Today, of course, 10X is very good at trapping, the midpoint, boiling point compounds. The Carbopac X is doing a very good job of trapping the mid-range, but when we get in some heavy molecular weight compounds, they can be a little strongly adsorbed there. In some of the weaker Carbopacs do a pretty good job with a broad range of compounds, but they don't do a very good job when the compound is a gas at room temperature.
Okay, and the next question we have is there an advantage of using an adsorbent with a mesh size smaller than 6080?
Well, we always gain a little more capacity by going to a smaller mesh size, but usually what happens is that little bit of efficiency we gain doesn't offset the problem that exists, is we usually can't get the flow rate we need with the smaller mesh size.
Okay, and we have another question here. Can glass tubes be used for passive sampling?
The answer is no, and the reason is there wasn't any development work done on those. And for example, the glass frit doesn't have the consistent hole sizes that we need to control the flow on a glass tube compared to like the stainless steel tube that has a stainless steel mesh screen that's very precise.
Okay, and we have another question here. What kind of components are linked to a background contamination with 10X adsorbent? Acetophenone
is one of those. Benzaldehyde is another. We'll also see benzene and toluene at times. But acetophenone is the one that you'll notice the most.
Okay. What about the life of adsorbents, cycle of absorption, desorption?
We're kind of saying that the lifetime of a tube is 100 cycles plus or minus 50, which is not always what the customer wants to hear, but that depends how gentle the tubes are being handled. I mean, if the tubes are being shipped all over the world, we may only get 50 cycles. But if the tubes are localized to the place where the analysis and the sampling's taking place, it's well easy to get more than 100 cycles out of a tube.
Okay. Which applications is it best to select a glass thermal desorption tube over stainless steel?
I personally like glass because I like just to see what's going on in a tube. I can tell if there's any channeling happening. So I don't have a specific application chemically wise, but the times where we're going out taking important samples, it's nice to see what that tube looks like before and after sampling.
Okay, Jamie, well, I think that's all the questions we've got for you today. Thank you very much for your presentation. If any other questions do come in, I'm sure that Jamie will be happy to respond to them via email afterwards. Thank you also to our scientific partners in this webinar, being Sapelco Sigma Aldridge, for all their technical input and support. And with that, I'd like to thank you all for logging in and listening. Thank you and goodbye.